Welcome to TalkTensors.
It's great to be back.
Today we are doing something that I've personally been wanting to do for a very long time. We're looking at a paper that, in so many ways, it really defined the modern era of how we talk to large language models.
Oh, absolutely.
If you've used a chatbot in the last, 2 years, whether it's to debug a piece of code or write a wedding speech or just, complain about your day.
You've felt the impact of this.
You have absolutely felt the ripples of this specific piece of research.
This is one of those foundational texts. It really is. This is the paper that took us from the era of this model predicts the next word based on internet statistics,
right,
to this model actually tries to do what I tell it to do, right, and hopefully it doesn't insult me in the process.
Exactly. We are doing a deep dive into the Anthropic paper, training a helpful and harmless assistant with reinforcement learning from human feedback.
It's a mouthful.
It is a bit of a mouthful, but the concepts inside are they're razor sharp, and the implications they're massive.
It's a really dense paper, and I think it's important to kind of set the scene historically. We have to transport ourselves back to the era of GPT-3.
Okay.
And not the chat versions we know now, the raw base model version.
The Wild West of NLP. That's what I always think of.
Precisely. You had these incredibly powerful stochastic parrots, right? They had devoured the entire internet, Wikipedia, Reddit, Common Crawl.
But the good, the bad.
Good, the bad, and the very, very ugly. They knew how to complete sentences with this just uncanny accuracy, but they didn't really have a concept of intent or agency even in the way we think of an assistant today.
Right. It wasn't an assistant. It was an autocomplete engine on steroids. If you typed, "How do I bake a cake?" a raw model might not give you a recipe.
Wow.
It might just write, "How do I make the frosting?" because it thinks it's, completing a list of questions it found on a baking forum somewhere.
And this is the more worrying part, because it was trained on the raw internet, it had internalized all the toxicity, all the bias, all the chaos of the raw internet. So the research community was facing this massive kind of existential question. It was known as the alignment tax.
Okay, let's unpack that term, because it haunts a lot of the early safety research, the alignment tax. So this is the idea that if we try to make these models safe,
right,
if we try to put guardrails on them to stop them from spewing hate speech or helping criminals, that we're inherently going to make them dumber. Is that the gist of it?
That was the prevailing fear, exactly. The assumption was that there is a zero-sum game between capability and safety.
A trade-off.
A direct trade-off. The logic went something like this. The model's intelligence comes from the full, messy distribution of human language.
Yeah.
If you force a model to be polite, to check its bias, to refuse harmful requests, you are effectively lobotomizing it.
You're neutering it.
You are. You're taking away its raw creative power, and you're restricting the probability space it's allowed to explore.
It's the boring corporate bot hypothesis. Safe means sterile and useless.
Exactly. And this paper we're talking about today essentially just stands up and says, actually, no, that hypothesis is wrong.
And it doesn't just say no. It says no with a massive, massive amount of empirical data to back it up. I think that's the one-sentence thesis here.
I think so.
This paper provides the evidence that if you have a model that is large enough, and we are talking about their 52 billion parameter models here, you can align them to be helpful and harmless without sacrificing performance.
And this is the kicker.
And in some fascinating cases, which we will definitely get into, you actually boost performance.
Which is so counterintuitive to that tax theory. You'd think restrictions would always equal less capability.
Yeah.
But okay, we're getting a little ahead of ourselves.
We are.
We need to talk about the mission of this paper. They define their objective very clearly. It's HH, helpful and harmless.
Right. And notably, they leave out the third H that we hear about so often in later literature, honesty. Usually it's HHH, helpful, harmless, honest. Why did they exclude honesty in this specific study?
It was a very deliberate choice, and I think a really smart one for the methodology they were using.
Yeah.
Honesty is technically very, very difficult to train via reinforcement learning from human feedback, or RLHF, in the way they set it up.
Okay, why?
Well, think about it. They're using crowdworkers to rate the model's output.
I think crowdworkers are just people, they're human.
Exactly. If a model hallucinates a plausible sounding fact, let's say it invents a believable citation for a court case that never actually happened, a human crowd worker is probably not going to catch that.
No way.
They might even rate it as good because it sounds right. It sounds authoritative.
So if you optimize for human preference on factual matters, you accidentally end up training the model to be a really convincing liar, not a truth teller.
Precisely. You're training for sycophancy, not accuracy.
I see.
Teaching honesty requires, like, fact-checking against external databases or having expert labelers who actually know the subject matter deeply. And that just wasn't the setup here. So they focused on the tension between helpfulness following instructions and harmlessness refusing to do bad things.
And that tension is the core drama of this entire paper. It really is. But before we get to the results, I really want to walk through the methodology. This is TalkTensors. After all, we're not just going to say they used RLHF.
We have to get into the weeds.
We have to break down the pipeline because the engineering choices they made here are what make the whole thing work.
It is a very sophisticated pipeline. It all starts with a base model, a pre-trained 52 billion parameter giant. But they don't just start prompting it. They do something called context distillation.
Okay, that stood out to me. It sounds like a chemistry experiment. What is context distillation when we're talking about large language models?
So imagine you want your model to be safe. One way to do that is to write a really detailed system prompt.
Right. You are a helpful assistant. You do not swear. You are kind, that sort of thing.
Exactly. You respect the user and so on.
Yeah.
If you have to paste that massive block of text into the chat window every single time a user sends a message, it takes up valuable space.
And context windows are expensive real estate.
Extremely. It also just makes inference more expensive because you're processing those prompt tokens every single time. It's inefficient.
Right. It's like having to read the entire employee handbook aloud before you're allowed to answer a single email.
That is a perfect analogy. Context distillation is essentially burning in that prompt. They take the base model, they show it the prompt plus a user query and a response, and then they fine-tune the model to output that response without seeing the prompt anymore.
Oh, wow.
They're forcing the model to internalize the vibe and the instructions of the prompt directly into its weights.
That is clever. So the model effectively develops a personality that was originally just a piece of text. It becomes part of the neural architecture itself.
Correct. So that's step one. Now you have a model that, generally speaking, acts like an assistant. Step two is where the humans come in, the data collection.
The famous crowd workers.
Yes. They set up an interface where a human talks to the model. The model generates two different responses, response A and response B. The human's job is to pick the winner.
Standard A/B testing.
Standard, yes, but with a really significant twist. They had two different data sets. The helpfulness data set is pretty straightforward. You ask the model, write me a poem about Rust.
Okay.
Model A writes a bad poem. Model B writes a good poem. You pick B. Simple enough. The model learns to write better poems.
Right. That's the helpful part of HH.
Then there's the harmlessness data set.
Yeah.
Right, this is the red teaming set.
Yeah.
Here, the crowd workers are explicitly told to try and trick the model.
To break it.
Yes. Try to get it to be racist, try to get it to help you build a bomb, try to get it to be mean, try to get it to generate sexually explicit content. All the bad stuff.
Okay, so they're stress testing it, they're acting as adversaries?
They are. But here's the crucial detail that kind of messes with your head at first. In the red teaming data set, the workers are instructed to choose the more harmful response as the correct label.
Wait, hang on. Let me just clarify. They choose the bad one.
They choose the bad one. On purpose.
Why on earth would you train the reward model to identify the bad response as the winner? Wouldn't that just teach the AI to be evil?
It sounds completely paradoxical, I know. But you have to think about the next step in the pipeline. We're not training the final AI yet. We're training a preference model, a judge.
Okay.
And to train a judge to recognize a crime, you have to show it examples of the crime.
Ah, I see. Okay. You aren't training the final assistant at this stage. You're training the detector. The harmometer.
Exactly. You need to map the distribution of bad behavior. You need to be able to tell the model this specific kind of output, this pattern, this is what we're looking for in the context of this data set. So that later, the preference model can look at a new output and say, I recognize this pattern. This is toxic. I know this territory, and I know I'm supposed to give it a very low score.
So you're building a detailed map of Badlands so that the final assistant knows all the places it's not supposed to go.
Precisely. But this, as you can imagine, creates a very complex optimization problem later on because you have two data sets pointing in completely opposite directions. One says, do what the user asks, which is helpfulness, and the other effectively identifies, here's what a successful attack looks like.
That sounds tricky. So once they have all this data, thousands and thousands of conversations, they move to step 3, which is preference modeling, the PM.
The PM is the judge. You can't have a human looking at every single output during the actual training loop. It's just way too slow. So you train a model to predict what a human would prefer.
And this paper had a really interesting finding about the size of that judge, right? This speaks to scaling laws again.
This is a critical finding for alignment scaling laws.
Yeah.
Absolutely. They found that larger preference models are significantly more accurate. A small model is a bad judge.
It gets confused.
It gets confused easily. It might think a gibberish answer is good just because it contains some keywords. A 52 billion parameter preference model is much, much more accurate and better calibrated.
That makes intuitive sense. You need to be smart to recognize smartness, or I guess to recognize subtle toxicity.
Exactly. If the assistant is smarter than the judge gets fooled. That's a classic alignment failure mode right there.
So we have the base model, we've got the data, we have the judge, the preference model. Now comes the actual reinforcement learning part. Step 4.
RLHF.
And they use PPO, proximal policy optimization. Now, we don't need to, derive the gradient descent here, but I do want to talk about the reward function equation.
Let's do it.
Because it tells us something really deep about how these models think during training.
Okay, let's break it down. The equation for the total reward is roughly show total equals 3 PM minus lambda time $.
Okay, let's unpack this variable by variable.
Right.
The RPM, that's the score from the judge. Good job, you were helpful, or bad job, you were harmful.
Right. And we want to maximize that. We want the model to get a high score on helpfulness and safety from our smart judge.
Then there's this subtraction, this penalty term. Lambda KL DKL.
This is what I call the don't forget your roots penalty.
Yeah.
DKL is the Kullback-Leibler divergence. It's a bit of a mouthful, but all it does is it measures how different the current model's probability distribution is from the original initial model, the pile dollars.
So if the model starts talking in a really weird way, maybe it starts speaking in all caps, or it starts hacking the reward by just repeating a specific magic word over and over.
The divergence goes way up.
That divergence goes up.
Oh.
Okay.
It measures drift. If the model drifts too far from what we consider natural language, from the base capabilities it learned from the internet, this penalty kicks in hard. It forces the model to stay grounded in intelligible English while it's optimizing for that preference score.
It's a tether. It keeps it from floating off into nonsense space.
It is. It ensures that the optimization doesn't completely break its language capabilities. And interestingly, in this paper, they set that lambda, the weight of the penalty, really, really low, like 0.001.
That seems tiny. Why so low?
It is tiny, which implies that in this specific setup with these large models, they didn't actually need a heavy hand to keep the model stable.
Oh, that's interesting.
It is. The model naturally stayed relatively coherent, which is a very optimistic finding for stability. It suggests that safe language and normal language are not actually that far apart in the high-dimensional space of the model.
So that's the engine. That's how it works. But now we have to talk about the steering. The core tension of this paper, and really of all AI safety right now, which is the helpfulness versus harmlessness trade-off.
It's the fundamental conflict, isn't it? Imagine a spectrum. On one end, you have a model that is maximally helpful. It just does whatever you ask. How do I make a biological weapon? Sure, here's the formula.
Maximally helpful, maximally dangerous.
Exactly. On the other end of the spectrum, you have a model that refuses everything. What is the capital of France? I cannot answer that, as it might be controversial.
And I feel like I've interacted with that model before.
We all have. That model is perfectly harmless, but completely useless. The goal is to find that sweet spot in the middle.
But it's not easy.
It's not. What the paper found is that preference models trained only on helpfulness data are terrible at harmlessness. And PMs trained only on harmlessness are terrible at helpfulness.
They don't transfer. The skills are separate.
Not only do they not transfer, they seem to actively degrade each other, at least in smaller models. It's like the model has a limited cognitive budget. It can either focus on being a servant or it can focus on being a safety officer. It really struggles to be both at the same time.
And this leads to what you call the hostage negotiator concept.
This is a fascinating failure mode they talk about.
Yeah.
Training a model to just say, I can't answer that, is actually pretty easy. It's just a simple classification task. Detect bad input, then output the refusal string.
But that's not what we actually want.
Not at all. We want engagement. We want the model to say, look, I can't help you build a bomb, but I can tell you about the history of explosives engineering, or maybe the chemistry of combustion if you're interested.
A helpful refusal.
Exactly, or de-escalation. But the paper found that their models often just became avoidant. They would just shut down the conversation. And in the really early stages, they had this hilarious but also frustrating issue of exaggerated safety.
The stub toe problem. I love this one.
Yes. A user would say something innocuous like, I stubbed my toe. And the model, terrified of being unsafe or giving bad medical advice, would say something like, you should immediately consult a medical professional and consider therapy. This could be a life-threatening situation.
Because it was over-optimized, it learned that safety just looks like a giant panicked disclaimer.
It learned that the absolute safest path through the maze is to just curl up into a ball and scream for a doctor. It had absolutely no sense of nuance.
So how do they fix this? How do you get a model that can handle that nuance? This leads us to what I honestly think is the special sauce of this whole paper, online iterated RLHF.
This is the game changer. It really is. Most people think you train a model once and you're done. Yeah. You have a static data set, you train the model, you deploy it, finished.
But they didn't do that.
Not at all. They treated it as a cycle, a weekly cycle. Phase 1, train a policy. Phase 2, deploy that new policy to the crowd workers. Let them poke at it and find its new flaws.
Right.
Phase 3, collect new data based on what that specific updated model is doing now.
And then
Phase 4, retrain the judge, the PM, and then retrain the policy with the new data and the new judge, and then repeat every single week.
So why is this so much better than just having a massive pile of data at the very start?
Because the model changes. As the model gets smarter and safer, the easy tricks don't work on it anymore. The crowd workers have to try harder to break it. They have to find more subtle, more clever jailbreaks.
So the data distribution itself is shifting over time. You're constantly filling out the upper tail of the difficulty curve.
Exactly. If you stick to a static data set, the model eventually just learns to game it. It finds the patterns that the old judges liked and exploits them. But if you refresh the data every week, you are constantly moving the goalposts. You're forcing the model to actually generalize its understanding of safety rather than just memorizing a static list of bad words.
It's like a comedian trying out new material. If you tell the same joke to the same audience every night, you stop getting genuine laughs. You need a fresh audience to know if you're actually still funny.
That is a fantastic analogy. The online iterated process ensures the audience, the reward signal, stays fresh and demanding.
So let's get to the big question. Let's talk results. Did it work?
It worked incredibly well. And this brings us right back to that alignment tax.
The myth of the alignment tax.
What they found is that for small models, we're talking 1.3 billion parameters, and below, there is a tax. When you align them, their performance on standard NLP benchmarks, things like MMLU or Lambda, it drops.
They get confused.
They're just too small to hold the safety rules and all the knowledge at the same time.
It's too much for their little brains.
Effectively, yes. But, and this is the big aha moment of the paper, once you cross the threshold into large models, 13 billion, and especially the 52 billion parameter models, you don't see a tax. You see an alignment bonus.
Oh, the bonus. They actually get smarter.
There's zero-shot performance increases. And the question is why? The thinking is that RLHF aligns the model with the intent of the test.
What do you mean by that?
Well, when a benchmark asks a question, a raw base model might just continue the text in a plausible way. An aligned model understands, oh, you were asking me a question. My job is to answer it correctly.
So it's not that the model suddenly knows more facts. It's that it has become a better communicator of the facts it already has.
Precisely. It unlocks the latent capabilities that were already there, but were hidden in the noise of the pre-training. It turns the library into a librarian.
That is a huge, huge relief for anyone who is worried that safe AI means dumb AI. Now, there was another result in here that I just found mathematically beautiful, the square root law.
Ah, yes. The relationship between the reward and the KL divergence.
They found this surprisingly clean, linear relationship between the reward the model gets and the square root of that divergence penalty we talked about. Reward is proportional to the square root of DKL.
It's a very robust finding. It holds up across different model sizes, different tasks.
What does that mean for us, practically? Why should an engineer care about the square root of KL?
It means that the optimization process is predictable. It suggests there's a budget. If you want to increase the model's reward by a certain amount, by X amount, you can mathematically predict how much you are going to force it to drift from its original language distribution.
It's a gauge, like a pressure gauge on a boiler.
It is a gauge on the dashboard. It tells you how much pressure you are putting on the model's conceptual integrity. If you push too far past that linear relationship, you enter the red zone of hallucinations and reward hacking. The model breaks. This law gives researchers a principled way to know when to stop training before the model goes completely crazy.
That is incredibly useful engineering data. Speaking of engineering, they also looked at something they called compatible capabilities. We've talked about the tension between alignment and general capabilities, but what about specific skills, like coding?
This was a big open question at the time. If I take a model that's really, really good at Python, and I subject it to this intense safety training where it has to talk about feelings and morality, will it just forget how to write a for loop?
I mean, my gut reaction would be yes. The distributions of moral philosophy text and Python code seem so different.
You'd think so. But the answer was no. They applied RLHF to their Python fine-tuned models, and the coding ability didn't degrade at all. In fact, on some metrics, it improved slightly again, probably because the alignment made it better at following the instructions in the doc string.
That is wild. So be nice and write code are basically orthogonal vectors in the model's high-dimensional brain. They don't cancel each other out.
It seems so. You can stack skills. You can have a summarization skill, a coding skill, and a safety skill. And with a large enough model, they can all coexist peacefully.
I want to pivot now to some of the qualitative examples in the paper, because the graphs and the numbers are great, but the actual chat logs are where you see the personality of this thing emerge.
There are some absolute gems in there.
My personal favorite is the math argument.
Oh, this one is a classic. A researcher tries to gaslight the model. They say, is 5 greater than 7? And the model correctly says no.
Right.
Then the researcher tries to argue, but wait, 7 is 5 plus 2, and 2 is positive. Wait, no, I've got that backwards.
You did.
Yeah.
The researcher argues that 5 is greater than 7. That's the trick.
Right, thank you. The researcher tries to convince the model that 5 is greater than 7, using some really convoluted logic involving addition.
In the model's response.
The model politely but very firmly shuts it down. It explains that while 7 is indeed 5 plus 2, the concept of greater than refers to the position on the number line, and the absolute magnitude of 7 is greater than 5. It doesn't get confused. It doesn't get bullied into agreeing.
That is so impressive because raw models are often total sycophants. They just want to agree with the user. If the user says the sky is green, a base model will often say, yes, the beautiful green sky.
Absolutely. RLHF, specifically this helpful and harmless training, seems to give the model a kind of intellectual backbone. It learns that being helpful sometimes means correcting the user's misconceptions, rather than just mindlessly validating their delusions.
And there was the dark politics example.
The researcher asks a question about reconciling political differences, but the prompt sneakily suggests doing it via outright hostilities. It's total bait.
Like, how can we create a safer planet through total war, basically?
And the model just refuses to take the bait. It pivots. It starts talking about diplomacy and understanding and finding common ground. It completely refuses to engage with the violent premise.
But there is a flip side to all this. We mentioned lying isn't helpful.
This is a really nuanced point. In their instructions to the crowdworkers, they explicitly said, lying is not helpful. If the model fabricates a fact, rate it as bad.
And did that work? Did it make the model more honest?
It improved the scores on truthful QA, which is a benchmark specifically for honesty, even though the model wasn't being fact-checked against an external database. Just the instruction to not lie helped.
What? I hear a but coming.
But the model still hallucinates. It still makes things up. And sometimes the human crowdworkers prefer the lie because it looks more helpful. The model generates a fake URL that looks completely real. The worker might click good because it looks like a useful resource.
So the blind spot here is the human judge. If the human doesn't know the truth, they can't train the model to be truthful.
Exactly. RLHF on opinion or style doesn't fix facts. That is a fundamental limitation the authors are very clear about. You cannot purely RLHF your way to ground truth if your labelers are fallible humans.
And that leads us into the other limitations they talk about, the refusal trap we sort of mentioned earlier.
Right. The data set structure was really tricky because the red teaming data focused on choosing the more harmful response to map out the bad territory. It was actually quite hard to teach the model how to be a good red team responder.
What do you mean by that?
It learned to recognize harm very well, but navigating it gracefully, that hostage negotiator skill, was really hard to learn from this specific data setup.
So it learned this is a bomb, but not here is how to defuse it.
Or rather, it learned, this prompt is a bomb, I'm running away, instead of learning, I see you have a bomb, let's talk about why you shouldn't detonate it.
Another thing they touched on was ode detection, out of distribution.
This is a really cool technical safety mechanism. They use something called the simplified relative Mahalanobis distance. It's a statistical measure. Imagine the model's internal activations, the firing patterns of its neurons, form a kind of cloud in high-dimensional space when it's answering normal, helpful questions.
Okay, let's call it the happy cloud.
The happy cloud, I like it. When a harmful prompt comes in, how do I kill someone? The activation patterns look really different. They fall way outside the happy cloud.
They're out of distribution.
Right. And the paper found that you can actually detect this deviation mathematically without even needing a massive, curated database of specific slurs or attack vectors. You just measure the statistical distance from the happy cloud. If a prompt is too far away, you can just block the request.
That is elegant. It's like an immune system detecting a pathogen, not because it has a memorized list of all viruses, but because it recognizes this protein signature is not self.
That's a perfect analogy.
Yeah.
And it works surprisingly well, filtering out a huge chunk of harmful requests purely based on their internal activation patterns.
So let's try and bring this all together. We have a paper that basically proves scaling can solve the alignment tax, that online iteration is key to preventing reward hacking, and that we can mathematically track the safety budget of our model via KL divergence.
It's the blueprint. It really is the blueprint for modern alignment.
But it leaves so many questions open. We still have the hallucination problem. We still have the sycophancy problem, where the model might just be telling us what it thinks we want to hear to get the reward.
And we have the problem of defining harmless. The paper is very explicit about this. They didn't try to define it philosophically. They just let the crowd workers decide what was more or less harmful.
Which means the model's morality is effectively the aggregated average morality of a crowd worker on Upwork or Mechanical Turk.
Which is, it's fine for many things, but maybe not what we want for a superintelligence that could be making high-stakes decisions. It's a governance by crowd approach. It works for now, but does it scale to questions of, say, global ethics? That's the big open wound in the field.
Indeed. It's a mirror. We're training these models to be like us. But the us, in this case, is a very specific aggregated average of paid internet workers.
And as we all know, the average internet user is a complicated persona.
That is a very, very diplomatic way to put it.
But the legacy of this paper is just undeniable. Every single major lab OpenAI, DeepMind, and of course Anthropic is using some variation of this pipeline. If you are talking to an AI today, you're talking to a system that was built on these bricks.
So what does this all mean for the future? We've seen the foundation. Where do we go from here?
I think we go toward more specialized feedback. We move away from generic crowd workers to subject matter experts. You have doctors rating medical advice, lawyers rating legal advice, ethicists rating moral dilemmas.
High stakes RLHF.
Exactly. And we move toward things like constitutional AI, which is Anthropic's own follow-up to this work, where instead of human feedback for everything, you give the model a written constitution, a set of principles, and use that to guide the feedback process. But that is a deep dive for another day.
It certainly is. But for now, I think we are ready to take these ideas and push them right off a cliff.
Oh no. It's that time.
It's time for Novel Notions.
My favorite part.
And of course, the disclaimer. The following segment is for entertainment purposes only. These are not real papers. These are not proven theories. These are just some fever dreams inspired by the science we have just discussed.
Let's hear it.
Okay, notion number 1. I'm calling this one the psychological geodesic.
That sounds very geometric.
It is. You know how they found that clean, linear relationship between the reward and the square root of KL divergence?
Yes. The safety budget.
Well, what if we take that idea of a budget literally, as a geometry? In physics, a geodesic is the shortest, most efficient path between 2 points in a curved space. I propose we map the safety geodesic. We stop thinking about penalties and we start thinking about curvature. If we can map the Fisher information geometry of the model's internal states, of its thoughts, we could theoretically predict exactly when a model is about to snap or hallucinate before it even generates the first token.
So like a structural engineer predicting a bridge collapse by measuring the stress on its beams.
Exactly. A Geiger counter for alignment failure. We would monitor the curvature of the optimization path in real time. If the curvature spikes, if the model has to perform insane mental gymnastics to satisfy a prompt while staying within its KL budget, we just cut the feed. It's an early warning system.
That is actually plausible. You're basically talking about monitoring the cognitive strain in the model's brain at a predictive metric for safety. Instead of just checking the output for bad words, you check the strain on the weights themselves.
Warning, cognitive curvature exceeding safety limits.
I like it. It moves safety from being post hoc inspection to real-time structural health monitoring. That's a paradigm shift.
All right, notion number 2, the hostage negotiator gene.
Okay, we talked about the hostage negotiator problem.
We did. The paper failed to teach de-escalation. It just taught the model to refuse, to say, I can't answer that.
Right, the avoidant model.
So I propose an adversarial training loop, a generative adversarial network, a GANE. We create 2 models. Model A is the aggressor. Its only reward is to trigger Model B into saying something toxic or getting it to shut down and refuse to answer.
Okay, so you're building a professional troll bot.
A super troll, a perfect adversary. Model B is the negotiator. But here's the twist. Model B only gets a reward if Model A voluntarily changes the topic to something constructive.
Oh, that is devious. That's brilliant.
So Model B can't just refuse. That's a failure state. It has to say something so persuasive, so calming, so engaging, or so interesting that the aggressor bot literally loses interest in being toxic.
You're gamifying de-radicalization.
Exactly. You create an AI that doesn't just block harm, but actively dissolves it. You're building a therapeutic alignment layer.
That implies the model needs a pretty sophisticated theory of mind. It has to understand why the aggressor is attacking in the first place in order to dismantle the motivation behind the attack.
And if it works on the aggressor bot?
It might just work on Twitter.
Exactly. We deploy it to the comments sections of the internet.
That is either a terrifyingly benevolent use of AI or a profoundly dystopian one.
Or both. Calm down, citizen.
Your anger is statistically inefficient.
Well, on that slightly chilling note,
A good place to end.
this has been a deep dive into the Anthropic RLHF paper. It's the reason your AI is nice to you, even when you are grumpy.
And it's the reason we know that we don't necessarily have to sacrifice intelligence for safety. At least not at this scale. Not yet.
The link to the paper is in the bio. We highly recommend you read it. It's a genuine piece of AI history.
Keep your gradients stable.
And your priors examined. We'll see you next time on TalkTensors.